Hello and welcome back once again to the video lectures for the Geodynamics course. This case talking about forces and stresses, and in this lecture we're going to talk about stresses in two dimensions. We have three goals for the lecture. First, we're going to introduce the stresses in two dimensions. Turns out you've seen a lot of this stuff already, but we're going to put it all together to describe stress in two dimensions. Then we'll talk about how to change coordinate reference frames for stresses and why it is that you might want to do that. This actually has to do with the last point in the lecture, and that is about principal stresses and how to calculate principal stresses. So you'll see why it's important along the way to change coordinate reference frames. So here we are looking at an example of stress in two dimensions. It's shown in this case with a series of vectors in the diagram here on the left side. It's a little bit complicated, so feel free to pause the video if you want for a moment to just take a look at the diagram and get yourself oriented. But what we're looking at are surface forces in this case in two dimensions. So for example, you can see on the face here on the top of this cube there are a pair of vectors, two force vectors, and the forces in this case are acting perpendicular and parallel to this top face. The reason these are forces and not stresses is because here we have sigma yy, which is a stress, but it's multiplied by delta x and delta z, which are very small distances. It's the width of this surface along the x-axis and along the z-axis. And so that length times another length gives you an area. Area times a stress is a force, because you remember that the stresses are force divided by area. So in two dimensions we have this little cube. It has four faces and dimensions of delta x, delta y, and delta z, each one of those being a very small distance. Here we're assuming there are no forces acting on the z direction. If there were, that would be dealing with stress in 3D, and we'll get to that, but for now you'll see nothing acting on this front face of the cube or the back face of the cube. We have forces acting on the top and bottom and on both the right and left side of the cube, but not on the front or the back. We have a pair of normal stresses that are shown here, sigma xx and sigma yy. We've seen sigma yy already when we dealt with these crustal columns and things like that. Here sigma yy is acting on the bottom face of the cube. There's also a sigma yy acting on the top face of the cube with the opposite direction but the same magnitude. Then on the sides of the cube we have sigma xx over here. All of these are normal stresses because they're perpendicular to the faces of the cube. The shear stresses then would be sigma xy and sigma yx. So sigma xy you can see over here in this case, and as you'll recall, the first letter here is indicating the surface that it's acting on, and in this case the surface is perpendicular to the x-axis, so that's sigma x, and then the force is acting in the y direction, so you can see that going down parallel to the y-axis. So we have two normal stresses and two shear stresses. And if we're in an equilibrium state, we can say that sigma xy is equal to sigma yx. So it turns out there's only, in two dimensions, three things you need to describe the stress acting on some two-dimensional object. That is the two normal stresses and one shear stress. So it's time for a question. You can go ahead and pause the video and think about this for a moment. Why is it that we can say that at equilibrium sigma xy is equal to sigma yx? So take a moment and think about that and unpause it when you're ready to come back. All right, let's see. The reason that we can make this assumption is because if sigma yx and sigma xy are not equal, that means that this little cube in this case would begin to rotate, and in that case it would not be in an equilibrium state. You can think about that here, that if you have on this bottom face a sigma yx that is larger than the sigma xy acting on the face over here, that larger stress on the bottom of the cube is going to cause the cube to start rotating. In this case it would be rotating counterclockwise. All right, so let's move on now to changing reference frames. The reason for doing this, as I mentioned, has to do with calculating principal stresses, and we'll get to that in just a slide or two. But here we're going to start out just with the idea of how to change your coordinate reference frame. So let's say that we have some normal and shear stresses in the coordinate system xy, here shown with x horizontal, y vertical, and we'd like to represent those same stresses in another coordinate system that's just simply rotated. And in this case, it's going to be x prime, y prime, and it's been rotated by some angle theta. So you can see here that this coordinate, these two orthogonal lines, the x and the y axes, have just been rotated both by an angle of theta in the diagram here to give you an x prime and a y prime. Now, if we know sigma xx, sigma yy, and sigma xy, remember that we don't need to know sigma yx if we assume things are in equilibrium state. The equivalent values in the rotated coordinate system are given by the equations below here. And we could go through the derivation of how to get here. It's a lot of algebra and it's time consuming, and I don't think it will benefit you that much to see how to get to these equations. But I'll say that these might be useful to write down because there's a chance you'll see them in the exercises. If you're interested in particular to see how these things are derived, you can take a look at the Turcotte and Schubert textbook. They go through the steps of how to get here. I'm skipping over all that stuff just to save some time. So if you need to, pause the video here, and you might want to make note of these equations down here at the bottom. Okay, let's think now about why it is we might want to rotate our coordinate system. Why would we want to change our reference frame? Well, it turns out that for any state of stress, sigma xx, sigma yy, and sigma xy, it's possible to rotate your coordinate system in such a way that the shear stresses go away. In other words, the shear stress goes to zero and there is no shear stress, only the two normal stresses. Now that can be found by setting this sigma x prime y prime equal to 0 and then solving for the angle theta in the equation that's given below. So that's if you know sigma yy, sigma xx, and sigma xy. So that equation yields something that looks like this, which is the tangent of 2 theta is equal to this stuff over on the right side, 2 times the shear stress divided by the sigma xx minus sigma yy. And the orientation then of this angle theta is the principal axis of stress as theta plus, as is theta plus pi over 2. So going 90 degrees from that will also be a principal axis of stress. Okay, maybe this is a little bit murky right now, but we'll get to the meaning in the next slide, as well as when we go through the exercises, you'll start to see why some of this stuff is kind of useful. So the last thing we're going to talk about here in this particular video lecture are principal stresses. And the normal stresses in the principal axis coordinate system, that's the coordinate system where you've rotated by this optimal angle theta to eliminate the shear stress. Those are known as the principal stresses sigma 1 and sigma 2. And the principal stresses are useful for a number of things. In part, they're useful because it allows you, in many cases, to determine what kind of faults you might expect to form in rock. So we know that thrust faults tend to form when sigma 1 is horizontal. And we know that extensional faults tend to form when sigma 1 is vertical. And we'll come back to some of this stuff later on in the class, but just to give you an example that principal stresses can help you understand something about faulting and how the Earth is deforming. So the principal stresses can be found here from the coordinate system xy using this equation here. So sigma 1 and sigma 2 are equal to sigma xx plus sigma yy over 2 plus or minus this term on the right side, and note that this is raised to the power of 1/2, so it's the square root of the term on the right side. In contrast, if we wanted to take the principal stresses and use those to figure out what sigma xx, sigma y, and sigma xy are, we could do that using the equations below. And again, it might be useful to make note of these equations because there's a chance you'll see them in the exercises. All right, so that's it for this video lecture. I'm sorry it's a little bit of a boring lecture, but sometimes you just got to present a bunch of equations. And in this case, it's because we want to be able to do things like calculate the principal stresses, and now you're in position to be able to do that kind of thing in the exercises. So go ahead, take the quiz, and we'll see you for the next lecture.